If vacuum solutions are defined by the condition that the energy momentum tensor of the matter fields vanishes identically, clearly non-vacuum solutions are characterized by a non-vanishing energy momentum tensor. The kinds of energy momentum tensors that are considered usually are those of some fundamental fields, in particular that of the electromagnetic field, and the energy momentum tensors of perfect fluids, characterized by the energy density, pressure, the proper velocity of the fluid, and so on. In this video, we are going to study one of the simplest non-vacuum solutions, which is static and spherically symmetric. In principle, we are going to determine the conditions for obtaining solutions of this kind, and then we will find a particular one which is characterized by the fact that the fluid, the perfect fluid, is incompressible. It has a constant energy density. This is a tremendous simplification, which is probably not very physical, but yes, it is a first approach, a first step towards a more physical solution, including more details on the behavior of matter. What this solution should be useful for is to characterize the gravitational field inside a star, for instance. So we have a spherically symmetric and we assume that also a static star, and we know that in the exterior you have this is the gravitational field. The exterior is vacuum by definition. This is what exterior means. It's outside of the matter distribution, so it is where d mu is 0. This is characterized by the Schwarzschild solution. So what happens inside? So this kind of problems you have, I'm sure that you have solved in electromagnetism. You have charge distributions of a certain kind, and you compute the electromagnetic field, usually electrostatic field, outside of the charge distribution. Then you compute it inside, and you have to impose boundary conditions here, so you go smoothly from one solution to the other. You glue them together, so you have the complete electrostatic field in the whole space. What we are going to do here for the gravitational field is exactly the same. Okay. Although the Schwarzschild solution, this is called the interior Schwarzschild solution. Okay, it's characterized by a constant energy density. We are going to work for the moment with a completely general energy density, imposing only the conditions of staticity and spherical symmetry, and then later on we will make the simplification that imposing that rho is constant. We have to, since the Einstein equations, remember they have this form, okay, and this is what we have to solve to determine the gravitational field. But for a perfect fluid, okay, there are no more equations of motion. We know that the consistency condition of this equation is that the divergence, well, this is 0 in this side automatically by virtue of the contracted Bianchi identity, and this has to be 0. Okay, but we know that this is on shell because this relation is on shell. Okay, and we found that this is proportional basically to the equations of motion of the matter fields. If there are no matter fields, for instance, if we are dealing with a perfect fluid, the condition that this is 0 is basically the definition of the equations of motion of the fluid. So we are going to have to deal with two kinds of solutions, with two sets of equations. On the one hand, we will have to solve first this equation, okay, these equations, and then we will have to solve the Einstein equations. Okay, so It's not just the Einstein equation separately, but you also have this condition, which is you have to do it because otherwise the solution you find would not be consistent. So let's start with this equation here. Okay, and remember first that T mu nu, okay, with for a perfect fluid, that this sign has to do with my conventions, is given by this expression. Sorry, minus in general relativity, where P is the pressure. It's isotropic pressure because it is the same in all directions. Then it is only characterized by a single number and not by three numbers. And rho is the energy density. That's well, how about u mu? U mu is the speed of the fluid. This is a speed field. It's a force speed, so it is something the fluid is supposed to have mass. It's not a radiation fluid or anything like this, so it satisfies this condition. If you take the covariant derivative, you will arrive to this identity that this is 0. Okay, so if I now take the divergence, I think in the lecture notes I do it the other way around, so with the indices up, okay, I have first P plus rho, this is projected with u mu and then u nu, plus P plus rho, the divergence of u mu times u nu, plus u mu u nu, and then minus nu p, because the metric is covariantly constant. And all this equal to 0. Now we are going to project this equation into the direction of the velocity. Okay, so I multiply by E nu everything. I take into account that u squared is 1. So what I get is u mu, nabla mu p, u mu, nabla mu rho, because everything is multiplied by 1. Here I get plus p plus rho, the divergence of u mu, plus, and here I get u mu u nu, nabla mu u nu, but then I use this property. I know that this is going to be 0. Okay, minus u nu nabla nu p, and this is equal to 0. We get cancellation between these two terms. Okay, and we get u mu nabla mu rho plus p plus rho, divergence of u mu, is equal to 0. Okay, this is the first equation, and now we can substitute this equation here in the original equation to simplify the result. So we have to split this, have p, and this is with nu, plus the next term as u nu, and then a minus p plus rho nabla mu u mu, plus nothing else, there's now the new p equal to 0. Okay, you see that this term cancels with this, and then we get well, we can combine the first and the last. Let me do it in this way. And then I will explain why this combination is interesting. Plus p plus rho u mu nabla mu u nu equal to 0. Okay. If we want, we can multiply the whole equation by minus, but this is really not relevant. Okay, so basically we obtain this equation by projecting in the direction of the velocity, and this direction by subtracting from the original equation this one. This means that this equation should be orthogonal to the velocity, and indeed, if you multiply this by u nu, you see that this gives you u mu minus u mu, so this vanishes, and the second term vanishes by virtue of this identity here. So indeed, this equation is orthogonal to the velocity. Now this is, if you recall what was the Euler equation, the form of the Euler equation, you see that this is the general relativistic Euler equation. Having decomposed the equation nabla mu t mu nu equals 0 into components parallel to the velocity and orthogonal to the velocity, now we are going to specify the velocity. Well, more than specifying the velocity is really a choice of coordinates. We are going to choose coordinates which are co-moving with the fluid. This means that the components will be proportional to delta mu t, so only t component, and the rest will be 0. I'm not saying that this is equal to 1 because we have to satisfy this condition, and this condition is this one. And if this is delta mu t, this means that there is going to be the component, the t component square times gtt has to be equal to 1, and then ut is going to be the 1 over the square root of gtt. Okay, so in total u mu will be delta mu t divided by the square root of the component gtt. This still doesn't tell us much about the fluid, it's just a condition on the coordinates. Now we can use this velocity in the first equation, okay, and it tells us that nabla t rho, this is a scalar, so I can already replace this by partial t, and this comes divided by the square root of gtt plus p plus rho, and the divergence of nabla mu, but we write it in this way. And then u mu, which is delta mu t divided by the square root of gtt. Okay, this has to be 0. Since this is, we have here delta mu t, in the partial derivative only the component t does something. So we see that if the solution is static will mean certainly that rho is just a function, is not a function of t, and we know that the metric will also be independent of t if this comoving coordinate is used as the coordinate associated, adapted to the isometry, okay, which is the case. So in this case, this equation is satisfied, and we only have to worry about the second equation. So let's work out the second equation. Well, let's start with the component nu equals 0. Nu is the free index of this equation. So we are going to split the equation into nu equals 0 and nu equal I being a spatial index. Okay, so we have nu equals 0 or t. I am using t, I think. I am using the metric that we obtained before, so it is diagonal. I put this assumption here that we are using not diagonal, but it doesn't have GTI components, okay, because of staticity. So this is another condition equal to 0. This came because staticity was the condition of stationarity plus hypersurface orthogonality, which translates into the absence of these crossed terms. This means that this has to be GTT. Now u mu and u nu only have t component. Okay, so these are the components that appear here, and we saw that it is equal to 1 over square root of t this squared, and then t component, because GTT, well, the index mu that we had here, it can only be t, and here u mu only has t component, so this has to be t. Okay, and again, this nabla can be replaced by a partial derivative plus p plus rho, and again 1 over gtt nabla t and ut. And okay, this is partial t plus partial t ut, which is going to be 0, plus ut t, and this is going to be, the only possibility is t because it is contracted with this. And well, for a static metric and for a static fluid, this is going to be 0, and this gamma is 0 because we computed before. The conclusion is that this equation is automatically satisfied also when the fluid is static and the gravitational field is static. Well, so far so good. Now let's consider the spatial components, nu equal to I. Okay, again, because there are no mixed terms, the only possibility is that this is Gij, and the part that depends on the velocities vanishes, so we only have minus Gij, and automatically we have the partial derivative with respect to J of the pressure plus P plus rho. Here we have u mu nabla mu, and we have the same as before, 1 over gtt, and nabla t of u nu, which is in this case ui. But okay, this is partial t ui. You would be tempted to set this automatically to 0 because you say that this is ui and the ui is 0. But as I have said several times before, really you should read this as nabla u and the components t and I of this thing, which do not have to be 0. Okay. The standard notation is this. This is, but it can be confusing, especially it can lead you to this kind of errors. So this is what you get. This is certainly 0, but here this component doesn't have to be 0, and this just gives you a square root of gtt. Okay, so this equation becomes minus Gij partial jp plus p plus rho divided by the square root of gtt gamma tti equal to 0. And this is the equation that still has to be solved because it is not implied by the requirements of staticity. We still haven't used the spherical symmetry, but it will not be solved automatically by that either. Now we have to consider the Einstein equations. The first thing that we are going to do is to write the metric in one of the forms that I give you in the previous video. I think it is the form B, but it doesn't really matter. But now you only need the only thing that you need to remember is that a static spherically symmetric metric depends on only two independent functions, which can be chosen in different ways, and this is one of them. Okay, it depends on only two functions of the radial coordinate r. If we want to compute to work with the Einstein equations, you need to compute the components of the connection of the Ricci tensor and of the Einstein tensor, which is done in they are given in the notes to simplify your life, but again I recommend you to do it on your own. So assume that you have computed with all these gamma mu rho and g mu nu, which is what you need. Okay, but in the right hand side of the Einstein equations you have the energy momentum tensor and you have to compute it. Remember that it has this general form, so this is p plus rho u mu u nu minus p g mu nu, and okay, clearly this is diagonal, so t mu nu is diagonal, and the components that you get are minus t tt, okay, is equal to p plus rho. So how much is u mu? U mu is g mu u nu, and the only possibility is that this is t and tt and t. Okay, so this is gtt, and remember that this was 1 over the square root of gtt, so this is square root of gtt. So you get here square root of gtt, which is lambda, this parameterization, and the lambda again because you have two u's, so you get lambda minus p and then gtt, which is lambda. Okay, these two terms cancel and you only get rho lambda. So let me write it like this, t will be minus rho lambda. Then the spatial components, p plus rho, since ui is 0, okay, then the only thing that you have is minus p gij, so dij is p gij, and this is the result. Okay, since we are using spherical coordinates, we can specify this a bit more. Okay, so this would be grr, and grr is minus p divided by mu, then t theta theta, and this will be minus p divided by multiplied pr squared, and then t phi phi, which is minus we can write it like sine squared theta t theta theta. Okay, just because g satisfies this property that g phi phi is equal to sine squared t theta theta. This means that we only need to take into account these three. These three will be independent because The same property is satisfied for the Einstein tensor. This is something that we discussed. Okay, so if the theta theta component is satisfied of the Einstein equations, then the phi phi component will be satisfied as well. Okay, now we have everything. Let me remove this calculation from here, and let's consider the TT component of the Einstein equations. GTT was computed, and you can write it in this way: lambda divided by r squared and mu minus 1 r prime, where a prime denotes derivation with respect to r, equal to 8 pi g, and then minus rho lambda. Okay, this means that this lambda and this lambda go away, and we have this equation equal to 8 pi minus 8 pi g rho r squared, and this can be integrated. Okay, this is just the r. So the standard way of doing this would be to multiply everything by dr, and you integrate these two sides, and this thing that you get here, okay, you are going to integrate, you replace r by some other variable. Okay, if you want to express this in terms of r, then you write this as an integral dx x squared rho of x, and you integrate between 0 and r, plus some constant that you choose according to your boundary conditions. This integral gives you something called the mass function. And this is because of the role it plays in the solution. In fact, this gives you that mu minus 1 is equal to minus 8 pi, divided by 4 pi, because this is supposed to be a volume integral, and then you would have to be you would have to integrate also over theta and phi, which is the solid angle, 4 pi. So sorry about this. Divided by r, and then mu is equal to 1 minus 2 gm of r divided by r. Okay, you would probably say that, okay, but you don't know what rho of x is because you haven't determined it, so you cannot perform the integral, and this is just blah blah blah. Okay, you are right. You can also understand this as a change of variables from rho to m, which is probably more useful. And in the case of the Schwarzschild solution, in which rho is going to be assumed to be constant, this integral can be performed directly, and then you know everything about mu. In any case, if you remember the Schwarzschild solution, you recognize that mu has exactly the same form with the constant mass of the Schwarzschild solution m replaced by this mass function m of r, and this is why it has this name. Now observe that GRR was given by 1 over mu, and GRR has to be negative, so mu has to be positive, and finite, which means that mu has to be different from 0. In total, this implies that 2gm of r has to be always smaller than r. This is a consistency condition that this mass function has to satisfy. Basically, it has to grow slower than r. Now that we have defined this mass function, we can replace everywhere rho by m or derivatives of m. In particular, gtt is given by minus 2 g m prime lambda, divided by r squared. For the r, we have minus the derivative of log lambda divided by r squared plus 2gm divided by r squared r minus 2gm. Okay, next we should consider g theta theta, but we are not going to need it because, and maybe I should have explained this before, g theta theta is related to gtt and grr in such a way that if the Einstein equations are solved for the components tt and rr, then they are for theta theta. This relation is based on the Bianchi identity, and we can, for instance, look at the r component of this Bianchi identity, and we could expand it just to show exactly how it works. The first term with a gamma can be written in this way, and then the second term, I think we have done this already a few times, is like this. Then here in the first term, the only non-vanishing component is with mu equal to r, because the Einstein tensor is diagonal, and so is the inverse Einstein tensor. And this second term, we can really expand it in this way, so it's gamma ttr gtt plus gamma rr grr plus gamma theta theta r d theta theta plus gamma phi phi r d phi phi. This is equal to 0. However, you know that g phi phi is related to g theta theta like this, and if you use the relation between this component and this component of the connection, you will find that the last two terms combine just with a factor of 2. It is not really very important that they combine in this way. The only thing is that you have g theta theta and some factor. The result is that if you read this equation, if you know gtt and grr, you know g theta theta. It is not independent. You could say that the relation, this is a relation between the left-hand sides of the Einstein equations, but it has to be identical to the relation of the right-hand sides for this to be useful, because it is not that just that d theta theta is related, but that this relation is the same relation that occurs with the energy momentum tensor. But indeed, this is what happens, because you have exactly the same relation for the energy momentum tensor. So you have the same here with TRR, with TTT, TRR again, and here theta theta. And now you multiply this, well, I'm not writing gammas and so on, you multiply this by 8 pi g and by minus, and you add this, and assuming that the R component, the TT components are satisfied, you see that this cancels, this term cancels, this term cancels, and what you have is gamma theta theta R multiplying the theta theta component of the Einstein equation. Okay, and now this is 0. But because this is this gamma is different from 0, what you get is that the other two equations imply the third equation, the theta theta equation. So summarizing, we are not going to need g theta theta, which is more complicated. The TT component has already been solved by this trick, if you want, so we just focus on this one. Okay. So let's focus on this one. I am going to write this now. TRR. Well, this we just wrote it. Tm divided by r squared, r minus 2gm, small m. Okay, and in the right hand side, sorry, I forgot g, we have 8 pi g and TRR, which we computed before, and which was minus p divided by mu. Okay, I just write this as an equation for lambda, a differential equation for lambda, and pack in everything. We have this 4 pi p r cube plus m. Okay, and this is an equation that we would use later, because if we know the mass function, okay, if distinguishing between the mass function and the total mass, plus the pressure, then we can find lambda by integrating this. Okay, yeah, which is essentially trivial. Okay, now we haven't yet solved the Euler equation, the R components of the Euler equation that we left here, and we can just consider the R component of this equation. Okay, the R component is minus gr, but then j has to be r as well, then partial r p plus p plus rho divided by gtt gamma ttr equals 0. Okay, so this is r, you want I equal to r of Euler. Now g lambda lambda, let me start with minus g r inverse. This is mu times p prime plus p plus rho divided by lambda, and then gamma ttr, which is a half of lambda prime mu. This is equal to 0. From this we can get another relation between p and lambda prime. You see that here this is log lambda prime, and we just can write this as p prime equal to minus a half p plus rho log lambda prime. But we know what the log lambda prime is, because we have it in this equation that we have derived before. Okay, and what we get is just p prime equal to minus g 4 pi r cube p plus m p plus rho divided by r minus 2g m. Okay, this is an equation which contains these variables, and this is known as the Tolman, who was one of the pioneers of general relativity. who is better known as the father of the atomic bomb and the director of the Manhattan Project, and Volkov. TOV equation, and which is the equation that determines the stability of a star. So this is a condition for hydrostatic equilibrium. We haven't explained it in this way, but well, we are basically studying hydrostatics in a gravitational field, which instead of being constant is spherically symmetric and dictated by general relativity instead of by the Newtonian theory. If you want to know why people like Oppenheimer and Volkov himself were involved in this kind of research, while they are better known for their research on nuclear physics and atomic bombs, you have to realize that stars are natural nuclear reactors, and the question of what happens at the core of a star is a question of nuclear physics, basically. How much can you compress the matter which is inside of a star is a question of how much you can pack nuclear matter, especially in neutron stars. So these people who were experts on in nuclear physics were naturally drawn also to this kind of problems. Here in this equation, if you know the equation of a state that gives you rho as a function of p or the inverse, then in principle you could integrate this equation. This equation of a state is determined basically by nuclear physics. So these people were experts on all these things, and they were applying their knowledge first to study stellar structure, which is basically what we are doing now in a very simple form, and this is what they did. They were the pioneers, so it's not that they were simple, but this was the start of this. And the moment the war started, these people had to apply their knowledge to something quite different. But before the war started, they made some very important contributions. One of them is related to this equation, and the other one is related to the collapse of a star. The first model, analytical model of gravitational collapse, which I don't think we will have time to study in this course. Schwarzschild basically considered the same equations, but in a very simplified case, in the case in which rho is constant. Okay, this is an incompressible fluid, because no matter what happens to the pressure, the density will not change. And in this case, first of all, the equations that we have derived are take this simplified form. So let me take this equation for p prime, and also this equation for log lambda. Okay, so the equation for p prime takes the form minus a half of p plus rho 0 log lambda prime, and okay, you see that we have p plus rho 0 here, but here only p prime, but we can add rho 0 because it is constant. Okay, with the prime it's just the same. Then we divide by p plus rho 0, and this is equal to minus log lambda 1/2 prime, and this is nothing but log rho p plus rho 0 prime and this means that we can integrate immediately. Well, we can do it in different ways as you want, For instance, we can first pass this to the left hand side, combine it inside of the derivative, then use the property of the logarithm. So this is just p plus rho 0 lambda 1/2 prime equal to 0, which integrates to some constant, and let me call this constant log a. Okay, remember this is an integration constant, and well, exponentiating both sides, we have equal to a, and then we have an equation that gives us p minus 0 lambda 1/2, so, and dividing, so this is just this. Okay. Okay, so what remains to be determined? We know now p as a function of lambda. We just have to find lambda and also mu. Okay. Mu was given in terms of this mass function, but the mass function can be found immediately in this case because, as I said, you can make the integral very easily. This is 4 pi, and the integral between 0 and r of the x squared and rho 0. This is just rho 0 times the volume of a 3 sphere of radius r. Sorry, interior volume of a 2 sphere of radius r. Okay. Then mu, which was 1 minus 2gm divided by r, is 1 minus 8 pi g divided by 3 rho 0 r cube. Okay, so we have found mu. We also have found m of r, and well, we can go back to this equation that we had for lambda. Okay, in this equation we know p as a function of lambdas. We can substitute. We know m, okay, which is here, so we can probably integrate the equation. Let's see what it looks like. So it is log lambda prime was minus 2g r minus 2gm 4 pi p r cube plus m. Okay, let me check that this is correct. No, I think I made a mistake here. This is just a simple r. Okay, so this is the equation, and now we start substituting. 2g r minus, now 2gm is 8 pi divided by 3 r cube rho 0, and this is 4 pi r cube a divided by lambda 1/2 minus 4 pi r cube rho 0 plus m, which we said is 4/3 pi r cube rho 0. I can take 4 pi r cube as a common factor. In fact, I think divided by 3 would be better, so I get 8 pi g and r divided by okay, factor of 3 here, and then 1 minus 8 pi, here g is missing, g divided by 3 r square rho 0. Okay, I had r cube here, but I have divided both by r squared, and I can multiply this by 3, and this becomes 3 8 by g. Okay, and okay, after taking this common factor, you get 3a divided by lambda 1/2 minus 3 rho 0 plus rho 0. Okay, this is just minus 2 rho 0 okay, if I take a common factor lambda 1/2, it takes this form. Now the left hand side is lambda prime divided by lambda, but I can since lambda, we have lambda 1/2 here, and it is probably the variable that will be used to integrate, then we can really multiply this by 2 and divide by and take the square root, and we have 2 times lambda 1/2 prime divided by lambda 1/2 equal to 8 pi g r 3 minus 8 pi g r square rho 0, and here 3a minus 2 rho 0 lambda 1/2, and everything divided by lambda 1/2. We have lambda 1/2 on the left and on the right. We can remove it, and now we take this, that is the only part that depends on lambda 1/2, to the left hand side, minus 2 rho 0 lambda 1/2, and okay, what we have achieved is that we have only lambdas and lambda prime in the left hand side and a function of r in the right hand side. Okay, this is not so difficult to integrate then, if we take the lambda as lambda 1/2 as the variable. This is the lambda divided by r, so let me write it like this, and the r on this side. Okay, sorry, the 2 I simplified. I write 4 1/2, and okay, I can make this. This is going to be what you have here in the numerator is basically the derivative of the denominator up to a factor that I just add. So I multiply this by minus 2 rho 0 and divide by minus 1 over 2 rho 0. So this is just minus 1 over 2 rho 0, the log 3a minus 2 rho 0 lambda 1/2. The right hand side, we also see that what we have in the numerator up to another factor is also the derivative of the denominator. So we also have minus 1 over 2 rho 0, and this will be the of 3 minus 8 pi g r squared rho 0. Okay, no, if I do it like this, I need a factor of 4. Okay, divided by 3 minus 8 pi, blah blah blah, which means I have the derivative of the log. Okay, well, I integrate as before, or just integrate both sides and up to a constant of integration. Okay, get that log 3a minus 2 rho 0 lambda 1/2 is equal to log 3 minus 8 pi g r squared rho 0 to 1/2. This is because I could have written this and then eliminated these factors in both sides. Okay, I plus a constant. Okay, a constant that I can write like the log of a constant, so I can put it here if I want. Now I exponentiate, so I eliminate the logarithms in both sides. Okay, and we're almost there because we have minus 2 rho 0 lambda 1/2 is this expression 3 minus 8 pi g rho 0 r squared 1/2 minus 3a, and I will divide by minus, so I get 3a minus this divided by 2 rho 0 and this squared. Okay, and this is the result for lambda. So let me summarize. Here we have lambda given in terms of integration constants, the Newton constant, the constant density, and nothing else. The rest are functions. Then we have mu, again given here by the density, and g. P is given by this expression. We can just replace the value of lambda and we recover P, and probably we'll have to do this explicitly at the moment. And okay, I think we have everything. Okay, so we have solved the Einstein equations, and now we have to start interpreting the result. So in order to do this, we have to determine this integration constant, and we need to use better variables than this constant density. Suppose that the radius of the star is r, okay, and not to be confused with the function r that we are using in certain coordinates. Here we are not using that function. This is not the Ricci scalar either, so this is the radius of the star. This means that outside of for r larger than r, t mu is 0. Okay, so this distribution ends at the value of the radius equal to r. Okay, this means that when I integrate and find the mass function, if I integrate for a value larger than r, what I get at some point is that 4/3 of pi r cube rho 0, because only the r is smaller than capital R contributes. This is what I'm going to get. The mass function will be some increasing function. It grows with the cube of the radius, but so this will be r, this is m, but at r equal to capital R, it doesn't grow anymore, and it is constant, and this constant is m, the total mass of the star. If we want to re-express, for instance, mu in terms of this total mass, it can be useful to have minus 2 gm r squared divided by r cubed. Okay, one thing that we have obtained immediately, even if we didn't search for it, is that when r is equal to r, okay, this mu is identical to the function that you have in Minkowski. Sorry, at the Schwarzschild solution, at the exterior Schwarzschild solution, which is something that we wanted, because we wanted a solution that continues, okay, that can be glued smoothly with the exterior Schwarzschild solution, and this is what happens here. You have r squared, capital R squared divided by capital R cubed, and this is exactly the function that you get in Schwarzschild for small r equal to capital R. And of course we want the same. We want for lambda. For lambda, what we want is that lambda evaluated at capital R should be equal to 1 minus 2 gm divided by r. Now, imposing this in this form of lambda, okay, we'll fix probably c. So let's just do the calculation. We have 3a, well, we also have that constant, 3a pi g rho 0, but rho 0 is m 3 divided by 4 pi and r cubed, okay, and then r squared, which is capital R squared. We are evaluating this function like that, and then we have 2 times again 3m divided by 4 pi r cubed, and all this, oh sorry, this comes with the square root, and this comes squared. Now we operate, okay, this we impose that has to be equal to 1 minus 2g capital M divided by capital R. Let's operate a bit to simplify this expression. This gives us get 2 here, and we can take this outside of the square. Okay, so this would be 2 pi r cubed divided by 3m squared, and all this expression squared equal to 1 minus 2 gm divided by capital R. Now we can multiply this by 3m divided by 2 pi r cubed, and we now take the square root of these two sides. Okay, so we have here 3a minus c, and 3 minus, there is another 3 times 2a, so it gives me 6 g m divided by r to the power 1/2. Okay, I can take a square root of 3 outside. Okay, and see that I have exactly the same, the same expression here and here. So I take this to the other side and I get 1 minus 2gm divided by r. Yeah, sorry, I erased this to power 1/2, but it was already squared, so okay, so this is 3m divided by 2 pi r cubed minus c square, sorry, plus c square root of 3, and if I divide by 3, this is the result for the integration constant a that allows us to glue the exterior and the interior Schwarzschild solutions. We still have one integration constant, which is not determined, which is this c. Okay, one of the things that another boundary condition that we have to impose is that the pressure at the surface of the star should be 0. Okay, looks like a reasonable physical condition, but this is given by a divided by lambda 1/2 evaluated at capital R minus rho 0, which is m is minus 3m divided by 4 pi r cube. Once we are using the total mass instead of the density, and of course we can immediately substitute a and lambda 1/2. Okay, but the lambda 1/2, because we just imposed that this should be the case, is given by this. Okay, and look here, you just take this is lambda 1/2 at r, so you take it here dividing, and the only thing that you have to replace here is the expression in brackets, which was m divided by 2 pi r cubed plus c divided by the square root of 3 minus 3m 4 pi r cubed. These two terms combine. This is just 2 and 4, so it's minus m divided by 4 pi r cubed plus c divided by the square root of 3, and we said that this has to be 0. This means that c is square root of 3 m divided by 4 pi r cubed, and this is the last integration constant that we have to determine. And now we can collect all the results, and let me just write the final form of lambda, the final form of mu, and the final form of the pressure. Okay, the density was given to us and it was constant. Okay, so we know it. So lambda, I'm not going to do the calculations because this is just simple algebra, is 1 minus 2gm divided by capital R 1/2 minus mu 1/2 square, and mu is 1 minus 2gm small r squared divided by capital R cube. Finally, P is given by 3m divided by 4 pi r cube, and this function that this factor that always appears everywhere, divided by lambda 1/2 minus 1. Okay, well, just for sake of completeness, R0 was 3m divided by 4 pi r cube. Okay, this determines the whole solution. P and rho are the variables that determine what is the mass distribution, the pressure, and so on. They determine completely g mu together with the metric, and lambda and mu were the only dependent functions of that appear in the metric. They were functions of r. Okay, one thing that we can investigate now is the value of all these functions at the origin. So the origin here is r equal to 0. And well, mu of 0, you can check that it is just, it's easy to see that it is 1. Lambda of 0 is 1/4, 1 minus 2 gm divided by r, 1/2 minus 1, and this square is also a finite number. And how about p? Well, p of 0 is this factor that has in front of it. There is 1 minus 2 gm divided by capital R 1/2. Lambda 1/2 has so what is the best way of doing this? Well, lambda 1/2 has first a factor of 1/2, and then you have 3 times this parenthesis that this parenthesis always means 1 minus 2 gm divided by capital R to the power 1/2 minus, and then mu to the 1/2, but this is 1. Okay. And nothing else because this was squared, and there is minus 1 here. Okay. And this is it. Now we simplify this. We multiply this by 2. Okay, and we take this as a common factor. So this case minus 3, this parenthesis to the 1/2 plus 1, and everything divided by this. So there is a cancellation. This 3 cancels with this. You have 1 minus this expression to the 1/2 divided by 3 times this expression 1/2 minus 1. Okay, so this is P at the origin. So how should we study this function that gives us the pressure at the center of the star? Since the mass of a star doesn't change a lot during the life of the star, well, up to supernova and so on. For instance, if we think about the sun, which will never become a supernova, the sun will lose up to 10% of its total mass in terms of energy, radiation of energy during its whole life. So it's irrelevant, in particular compared to the dramatic changes that the radius will suffer. So we should consider this as a function of the radius. And as you see, the thing that you always find here is the quotient 2gm divided by r. It is here and here in this parenthesis, which is the Schwarzschild radius divided by the radius of the star. Okay, we can also make this coefficient here function of the radius if we multiply by the mass. So we can write we multiply by 2g squared and 2g and divide by the same. So this is some overall factor that depends on the mass, and we get a factor of r s divided by r cube in front of this whole equation. Okay, so the natural variable, or the thing that we should study, is how this changes the radius relative to the Schwarzschild radius. First of all, remember that we had a condition on the mass function that was telling us that this had to be smaller than r. Now that we know that in this case we are studying constant the case with constant density, we know what m is, and if you massage this a bit, you will find that you can write it in this form: r divided by r Schwarzschild larger than r divided by r squared. Okay, the simplest way to satisfy this, okay, is if this is larger than 1 and this is in general smaller than 1, and you see that this has to be always smaller than 1 because r is smaller than the radius of the star. Up to that point, after that, it doesn't really matter. It becomes constant. This thing will become a constant. It doesn't matter. It is inside of the radius of the star where this equation counts. So for r, which is smaller than the radius of the star, we just need to pick an r which is larger than the Schwarzschild radius. Okay, so this is the first condition, and without that condition, the metric becomes singular. So we are considering stars which are larger than another star with the same mass and the Schwarzschild radius. Anyway, this clearly is related to gravitational collapse. Now you study this function as a function of the quotient between the radius and the Schwarzschild radius, you will see that this pressure is a growing function of this quotient, and that in fact it goes to infinity if you make all the calculations when r approaches, or if you want r divided by rs approaches this value 9/8. Then p0 goes to infinity, which clearly signals a sort of instability when you reach that point. So for constant mass, value of the mass, if you start compressing the star, which can happen when a star becomes old and it starts contracting, you see that the pressure becomes infinite, and this signals an instability that it tells you that gravitational collapse will start. Okay, this is a very simplified model, so don't take these numbers as really the end word. But this tells you that in a way, when the star with a given mass is compressed to a radius which approaches the Schwarzschild radius, the pressure will become infinite. I think that at the beginning of the course, when we talked about the energy momentum tensor of perfect fluids, we remarked the fact that pressure also gravitates and that it contributes to gravity, just like the energy momentum density. Like the energy density. Then if the pressure grows because you compress the star, there will be more self-gravitation inside of the star. It is not just that the energy density grows, but also that the pressure grows. Well, this doesn't happen in the Newtonian gravity. The pressure does not contribute. So at some point, it will become big enough to counterbalance the self-gravitation of the object. This doesn't happen in general relativity, and this means that there will be limits to how much you can compress a star, or if you look at it another way, how much mass you can have. So you can rewrite this condition in a completely different way, just using the relation between mass and density, and you see that the same condition tells you that when mass approaches this value, okay, this is just messaging these the same relations all the time. you have this instability that the pressure at the center becomes infinite. Well, this means that if you have a spherical symmetric matter distribution with of constant density, no matter how small it is, there is an upper limit for the amount of mass that you can have. Starting from that amount of mass, and here again, this is because we are now writing things in terms of a constant density, and m now is variable. There will be a certain mass for which the pressure at the origin becomes infinite. No matter how small this density is, there will be a gravitational collapse. And this is something characteristic of general relativity, as you know, the fact that there is this thing called gravitational collapse. There is some of the results can be formulated as a theorem, okay, which is a bit more general than the result that we have obtained here for a constant mass. So let me write it for you. It's in the notes, okay. Or let me read it. So there is no equilibrium configuration of a spherically symmetric star which is filled with a perfect fluid with a density which is a non-increasing function of R, and such that you satisfy this condition m of R is larger or equal than 4R divided by m, where this is the radius of the star and this is the mass function. Okay, so there are several things that one should study now. This gravitational collapse. The way to do it could be to consider, first of all, metrics or gravitational fields which are not stationary anymore, because a gravitational collapse will be a dynamical process in which the gravitational field will change with time, and we need a completely different ansatz. Okay, this is what in fact Oppenheimer and Snyder did in 1939, and they made the first description of gravitational collapse of a star. Then came the war, and then many years passed by before some of these results were taken seriously, and of course we haven't still observed directly a gravitational collapse, although it is widely believed that it is a physical process that takes place in the universe. We think that we have seen black holes, but we have to examine this from many different points of view, and this is really a hot topic of research. It's a pity that we don't have time to describe this Oppenheimer-Snyder gravitational collapse. You can find it in the book by Choquet-Brouillard. Okay, in a very condensed way, and you can also find the original paper by Oppenheimer and Snyder. The link is in the program. You just have to follow it. If you are at the IFT, then you can download the PDF of this physical review paper. If you are not and you don't know how to download it, just ask me and I will tell you how to get it.